All right, welcome everyone. In this first part of our geosteering workshop, we're really going to lay the groundwork. We're going to unroll the blueprint for technology that has completely changed the game in modern energy. And that is, of course, directional drilling.
So, here's our game plan for this session. First up, what is directional drilling really? Then, we'll look at the anatomy of one of these complex wells. After that, we'll get into the fun stuff, the driller's steering tools. We'll do a little head-to-head comparison, mud motors versus RSS, and finally, we'll tie it all together, showing how drilling meets geosteering.
Okay, let's jump right in. Part 1. What exactly is directional drilling, and how does it help us unlock all those resources trapped deep beneath the surface?
I mean, think about this for a second. How on earth do we drill for miles and miles underground, and not just straight down, but sideways? How do you even do that? This is the fundamental puzzle, the whole reason this technology was even invented. So here's the textbook definition, but what does it really mean? Well, the key takeaway is that it's intentional. This isn't accidental wandering. It's a very precise, very controlled process. You can think of it like a GPS for drilling underground. And I absolutely love that it's called a science and art, because that's exactly right. The science is the engineering, the physics, but the art, that's the skill of the driller adapting to what the rocks are telling them in real time. So why bother with all this complexity? Well, the reasons are huge. For one, you can get to reserves you could never reach otherwise. Think about a reservoir that's sitting under a city or a national park. You can also dramatically reduce the environmental footprint. Instead of dozens of well sites, you can drill, say, 20 or 30 wells all from one single pad. And here's the big one for us. You maximize contact with the reservoir. Instead of just punching one hole through it, you can drill along it for miles. It's a total game changer.
Okay, so now that we know why we do it, let's look at how it's structured. We're going to take a little journey down a typical deviated well and look at its anatomy. So take a look at this diagram. This gives you the big picture, the entire journey of a well, from the surface down to that horizontal target. Now, to really understand how drillers plan and execute this, you've got to speak their language. So let's break down the key parts of this path, one by one. Everything starts at what's called the kickoff point, or KOP. You've been drilling straight down, everything's vertical, and then you hit this pre-planned depth. This is mission control for the turn. It's the precise spot where you say, okay, time to start steering. It's the starting line for the curve. So once we kick off, we enter the build section. And the name says it all, right? You're building, angle. The best analogy is a highway on-ramp. You're smoothly curving, increasing your angle degree by degree until you're at the inclination you want. And how fast you make that turn? Well, that's called your build-up rate, or BUR. So you've built your angle, you're pointed in the right direction. Now what? Now you enter the tangent or hold section. Hold is a perfect word for it because that's what you do. You just hold that angle and that direction constant and drill straight ahead. And let me tell you, this section is often the whole point of drilling the well. This long, horizontal section, that's the money section. And what's the final destination for this whole underground journey? It's the target location. And this isn't just some vague area. We're talking about a specific point in three-dimensional space defined by coordinates and a specific true vertical depth, or TVD. The entire well plan is designed to guide the drill bit to hit this very precise bullseye. Okay, so we know the path. But how do you actually steer a metal pipe thousands of feet underground where you can't see a thing? It sounds a little bit like magic, doesn't it? Well, it's not magic. It's incredible technology. So let's open up the directional driller's toolbox and see what's inside. This secret to everything is something called the bottom hole assembly, or BHA. This is the business end of the drill string. It's way more than just the bit that's cutting the rock. The BHA is this carefully engineered combination of specialized tools, collars, and sensors. The specific design of this assembly is what gives us control over the well's trajectory. It is the brains of the whole operation. Now, when it comes to the steering technology inside that BHA, it really boils down to two main methods. First, you have mud motors. These are also called positive displacement motors. The second, more advanced method is called a rotary steerable system, or RSS, and these are a whole different beast. All right, so let's put these two technologies head-to-head, mud motors versus RSS. And this isn't just some minor technical detail. Understanding the pros and cons of each one is absolutely critical when you're planning an effective well. The difference in how they steer is just fundamental. A mud motor uses a technique called sliding. To steer, you actually have to stop rotating the whole drill pipe from the surface, aim a little bend in the motor where you want to go, and just push. You slide forward. RSS is totally different. With an RSS, the entire drill string is always rotating. The steering happens inside the tool. This has huge consequences. Because you're always rotating, you get a much smoother wellbore, and your overall rate of penetration is way, way faster. And these pictures give you a peek inside. On the left, that's the mud motor. The drilling fluid gets pumped down and forces that corkscrew-shaped rotor to spin inside the stator, which turns the bit. It's basically a hydraulic motor. On the right, that's an RSS tool. It's a lot more complex, almost like a little spaceship down there, with sophisticated pads that push against the wellbore to steer, all while the whole thing is spinning.
So what does all that high tech get you? Well, look at these numbers. This is from a case study comparing the two. Using a conventional mud motor, it took 23 days to drill this section of the well. 23! With an RSS tool, just 11 days. They basically cut the drilling time in half. And in this business, time is a lot of money, so the impact is just staggering.
Okay, so we've established that we have these amazing tools. We can steer a whale with incredible precision. But that brings us to the most important question of all, and it's really the whole point of this workshop. It's great that we can steer, but where should we be steering?
You see, directional drilling is the how. It gives us the physical tools, the raw capability to point that drill bit wherever we want it to go. It's the vehicle that lets us navigate the subsurface. But geosteering? Geosteering is the where. It's the navigation system. It's the science of using real-time geological data streaming up from the drill bit to guide that vehicle and keep it in the most valuable rock. And when you put the two together, you get this incredible, powerful synergy. Directional drilling is the car, but geosteering is the GPS with live traffic updates. Together, they make sure the wellbore doesn't just get to the right neighborhood, but it stays perfectly in the sweet spot of the reservoir for its entire journey, maximizing recovery. So, this leaves us with the big question that's going to drive the rest of our workshop. Now that we can steer with this amazing level of precision, what kind of geological puzzles can we actually solve in real time, right there at the drill bit? That's what we're going to dive into next, how we take this incredible capability and use it to turn geological uncertainty into a massive competitive advantage.